Okay, welcome to Jemmin Chang's W.I.S.E presentation. I'm looking forward to a great presentation. I know that Jemmin worked hard on this. He had a great mentor, Mr. Chris Petras, and he's going to say a few words, and then Jemmin will begin. Woo.
It's my pleasure to introduce you to a young man who has achieved an outstanding feat. I had Jemmin Chang as a student in last year's AP Physics class, where his intelligence and work ethic were clear and impressive. But even though I knew that Jemmin is very smart and works very hard on things, I couldn't have predicted that he would accomplish the incredible things he's done in this W.I.S.E project. Jemmin began working on an idea that he had for a W.I.S.E project in the fall. He was passionate and enthusiastic about it, but he ultimately decided that he should change his idea. He then had an idea of creating a program that would destroy any human, and maybe even other computer programs in the game Letterpress. I have little experience with computer programming, but I have enough to know that this would be a monumental task. As his mentor, I did my best to make sure that he knew this goal was going to be very, very challenging. Since I didn't know Jemmin's programming abilities, the amount of time he had to devote to this task, nor the complexity of the numerous difficulties that would undoubtedly arise as he embarked on this quest, I warned Jemmin that there was a significant chance that this would become an insurmountable undertaking. Nevertheless, Jemmin decided to go forth with his idea. I want you to understand two things before I introduce Jemmin. First, I want you to understand that despite the very real possibility of Jemmin's idea being either too difficult or simply unrealistic, Jemmin pushed forward, worked tirelessly, researched questions he developed, and formulated brilliant solutions to overcome the many obstacles that arose along the way. The second thing I want you to understand is that what Jemmin did is very, very, very difficult. When Jemmin would meet with me to tell me how his work was going and what new developments he made, I understood almost none of it, but I could tell that it was as challenging as I had predicted. As you listen to his presentation and you try to understand what Jemmin had to do to reach his goal, please realize that what he did is far more difficult than most of us can imagine. Please join me in welcoming Jemmin Chang.
Thank you, Mr. Petras. Welcome, everyone. Thank you for coming to my presentation today. If you have any questions during the presentation, feel free to just raise your hand and ask. We'll have time for questions at the end also. So I want to start by talking about why I took W.I.S.E. Last year, I knew basically nothing about W.I.S.E, but I saw my first W.I.S.E presentation in the spring of junior year. It was Erica Liu's presentation on 3D animation and actually working together with a friend who was doing music composition for her W.I.S.E project. And I just thought it was the coolest thing that they got to just design their own project. There were basically no requirements, no limitations, and it was very independent. And it seemed like a great thing for me to do in my senior year, especially because I had very few classes to take, a lot of extra time to devote to something like computer programming that I really enjoy. But my first project was actually not the one I'm presenting today. As Mr. Petras mentioned, I first wanted to tackle a game called Scrabble with Friends, which some of you may know I was somewhat obsessed with in junior year, always challenging everyone to play. And I wanted to still be better at it by building a robot for it. So I wanted to build a robot to play this game to get every single word in the game, essentially get the maximum number of points, so you couldn't possibly lose. Essentially, it ended up being just impractical because what I would need would be a robot pushing buttons at about the rate of 15 per second, and the Vex robotics that I was working with Mr. Fry were just not capable of something like that. And what I would need to purchase would be just too expensive. So I had to change my idea. So the first thing that came to mind when I knew I needed a new W.I.S.E project was this game Letterpress, which I'd recently started playing at this point. I really liked it. It's another word game. It's also played on a board. And some of you may know I used to play Scrabble competitively, so I'm very into word games. And the whole idea of writing computer programs to solve them has always fascinated me. I had done a project earlier for the game Hanging with Friends, which is much simpler. It's essentially Hangman. So that one just took a dictionary, looked through all the words, found the best ones, and solved the other person's words using a dictionary. fairly simple. Letterpress was going to be a lot more complicated, I knew. And for those of you who aren't familiar with the game, it's an iOS game. You can go and download it for free. And I'll go through some of the basic rules a little bit now. It's played on a 5x5 board of letter tiles. The object is to play words and capture the tiles, turn them to your color. So for example, if I played the word assortments here, those letters in assortments would turn blue, which is my color, and then my opponent would reply with a move. Non-systems, apparently to work. So they played non-systems, and you see that the tiles, even the ones that were blue, now turn to red. The dark red ones that you see in the corner there are locked tiles. That's one of the key aspects to letterpress strategy. Those locked tiles can't be converted back to blue tiles on my next turn. They're only temporarily locked over. So if I use the E, the S, and the N, the S and the T will become unlocked the next turn. But I won't be able to convert this S, S, and T on this turn no matter what word I play. That's one of the key aspects of the strategy. Some other rules that are very important. You can't repeat words. So of course you can't just keep playing the same word over again and taking the letters back. And you can also not play prefixes of previously played words. So if I played assortments in that example, my opponent or I couldn't play assortment or assort, anything that was a prefix of that previously played word. And so the strategy then is to play words that are not prefixes. So you would always play assortments, not assortment. Even if the S didn't give you any extra value, you always want to block your opponent from playing those other words. The game ends when the board is fully colored, and whoever has the majority of tiles wins. And it's a 25-tile board, so someone should always win. Okay, so one of the challenges of writing this program was that I had to create a graphical user interface, which is not something I've done before, don't have much experience with it. And graphics to me always seemed like a very tedious thing, at least in Java, which is the language I wrote this program in. So I wanted to tackle that and start learning it and really kind of get over my aversion for graphics. So I studied a lot with my Java textbook. I planned out the, we call it a GUI, G-U-I, Graphic User Interface. That's kind of a standard pronunciation of the acronym. So I planned this GUI based on another program called WordBiz, which is a Scrabble application. And it's a pretty simple interface, actually. I mean, there are a lot of buttons, but basically you have the board, you have the panel on the side with the messages, and sort of you can send people messages and such like that. And so I based my GUI on this simple design. The board is on the left, and what I call the interactions pane is on the right. The interactions pane has two states in Letterpress. Pretty simple. Just when it's your move and when it's your opponent's move. Your move is right here. It gives you the move choices, the top 5. This button here is to submit the move. For the opponent's move, you click the tiles on the board to enter the move, and then you click submit, and there's backspace clear if you make a mistake. So that was the basic graphics design. It actually took a lot more work than it might seem to take. The planning was very easy, but actually coding it was very tedious. A lot of bugs to fix. There's a lot more to the GUI than it kind of meets the eye. For example, each of these buttons and menu items needs a listener, which is what tells the program what to do when you click the button. So by itself, the button doesn't actually do anything, it just clicks. When I finally finished the graphics, though, I got to go on to the more interesting part, which is the actual logic of playing the game. So I basically separated this into 3 key steps. The first is getting all the possible moves on the board. That's this method, move choices. And when I say moves, it's a very important distinction. It's separate from words, because you can have multiple moves representing the same word. For example, if you have multiple A's on the board, you can use one A or the other A in the word, and it has a different strategic worth because the A's are in different positions. So I'll go into detail about each of these in a moment. The second part is finding the useful words. Useful words I define as words that are not subsets of others, and I'll show what that means in a second. And the last part is just finding the best move out of those useful words. And that's pretty simple. You find the one that gives you the highest value. So the first part, the move choices algorithm. I'm not going to go into too much technical detail. It is very technical. But basically, I have a trie structure, which is a branching tree of the dictionary. And it goes through the tree with the letters you have in your board and finds all the words you can make. So if I had all these letters in this trie section in my board, it would go through the first branch, go to the first branch, the end of the first branch, and get able, then ably, then go to the next branch off of A to get aces, aced, etc. And of course, they would generate a lot more words for an actual board. Usually, it was somewhere between 100,000 to 300,000 possible moves. So then the next part is where you narrow it down by finding the useful moves. Now, I'll talk about what a subset move actually is. For example, here we can play seats, which doesn't seem like that great of a word, because we can play masters, which includes all the same letters plus the M and the R. So that's why we call seats a subset of masters. It has tiles that are included in the other word, and the other word is longer. So you would never really play seats. You would always play the word that's longer, includes the other one. Now, that's very easy for a human to see that masters is better than seats, but the computer needs a logical algorithm to figure that out, because computers don't have intuition. So it needs to follow a series of steps, repeated steps, to figure out how this is a subset. And so I did it this way. This is a simplified example. With the actual program, it uses a 5 by 5 array of numbers, which represents the grid, the board. But here I'm just using a list of numbers. So those letters at the top are the letters that comprise those two words. And then the ones indicate the letters that are included in that word, and the zeros, the ones that are excluded. So you can see that masters includes all the letters, seats doesn't include all of them. So what you do is you basically take these two lists of numbers and subtract them. And then we see the negative ones indicate that seats is a subset of masters, because masters has all the same letters with the zeros, and then some, the negative ones. Now for a different case, we have a different result. We have grown and thrown. When we examine this and we subtract the numbers, we get negative 1, 1, and then some other stuff. And the reason why I didn't put the other numbers is because they don't actually matter. This is one of the key efficiencies of this algorithm, is that you don't have to process all the numbers. If you look at the first column, we see that thrown has E and grown doesn't. So we know that thrown is not a subset of grown, at least. Then we look at the second column, we see that grown has G and thrown doesn't. So grown is not a subset of thrown either. So once we have that negative 1 and that 1, we know that they're what I call unique, meaning neither of them is a subset of the other. They're both useful, and we should keep both of them in the useful list. So once we have the negative 1 and 1, we don't have to process the rest of the 23 letters, which helps speed up the algorithm. Okay, the next part is finding the best move. This is a fairly simple concept. The original game is represented by that first block there. Now we can't play the moves on the original game, or else it'll change the state of the board. So I make a clone of each of the games and play each word on a clone of the game, and then evaluate the end state of this board after this word has been played. And that'll be done for, usually the number of useful moves was somewhere around 10 to 20,000. So a large reduction from the 100 to 300,000 of the total move choices. The evaluation scheme for this algorithm is really simple. I just assign numbers to each of the colors. So a locked blue tile is worth 2, light blue 1, light red negative 1, and locked red negative 2. And you just add up the values of the colored tiles in the board. This board happens to actually have a total value of 0, if you calculate it. Okay, so once I finish all the algorithm work, I finally get to the long, fun process of debugging. And that's fixing all the things that are wrong with it. There's basically two stages to this. The first was fixing the compile time errors. And then the second was fixing the runtime errors. So compile time errors are essentially that the computer doesn't understand what I'm telling it to do. So it can't compile the code. It can take my written code and turn it into machine language. So most of those errors were pretty simple. They were syntax errors, so I missed a semicolon or I spelled the word wrong, something like that. So it wasn't that hard to fix that. After several hundred errors and a couple attempts, I eventually got it compiled. The runtime part, though, is the more difficult thing, because the runtime errors, the computer says that everything's working fine, basically. It's doing exactly what you told it to do, but it's not doing what you really mean it to do, because you told it the wrong thing. So you have to fix your logic. This will show you what happened when I finally was able to compile and ran it for the first time. That cursor is extraneous. I don't know why that's there, but the small cursor at the top, it's clicking the run button. That's the window it pops up. It works fine so far. I'm going to click the About button. The About information comes up correctly. Click OK. And now you'll see when I'm reading the information. When I click Game and create a new game, all that red stuff on the bottom pops up. Those are all runtime errors and exceptions that the program didn't expect. So I had to go about fixing all those. And that's a pretty long process. It takes a lot of sort of guesswork because you have to run the program, click a button, find a bunch of red statements, try to make sense out of them and figure out what's going wrong. With compiler errors, usually the computer tells you what's going wrong. So the compiler says, you missed a semicolon, something like that. It basically tells you what's wrong, so you can fix it. With the runtime errors, it's something more like null pointer exception. So it gives you sort of what went wrong, but in a very specific sense, and then you have to figure out what's wrong in your actual logic in your code that's causing the problem. But eventually, I did fix all those runtime errors. The first bug-free version was version 1.1, and once I had that completed, I could finally actually use it to play the game. And I decided to test it and collect some statistics to see, obviously it beats humans. I'm going to show you later, I'll play the program myself and get crushed. But I wanted to test it against other computers. There actually happen to be a lot of letterpress cheat apps on the App Store. You can go and find them, there are dozens. But I picked one in particular called Letterbrain because it was the smartest, easiest to use. A lot of the apps give you the word to play, but don't tell you which letters, which positions to play, so you can't always be sure. So I needed one that told you exactly what tiles to play, so you could be sure you're playing the move that it thinks is best. So these are the results of my test against Letterbrain. A lot of these games, because you're having two computers play against each other, take very long, much longer than human games. And so I wasn't able to play too many of them. Me and Rohit played 5 with Letterbrain going first, and 5 with me going first. And you can see the results there. It went surprisingly well, actually. I wasn't expecting it to do this well. It won 3 out of 5 going second, and 5 out of 5 going first. So that was very encouraging. Really good results. I was expecting it to lose most of the ones going second, because generally going first is a pretty big advantage in this game. But it went much better than expected. But of course, I still had a lot to improve with this program, because I had basically just finished the very basic algorithm, the very basic logic to it, and now it was time to make it more sophisticated. So the concept that I was using to make this program smarter than the Letterbrain or any other cheat app is something called Minimax. Oops. And Minimax is basically, instead of just looking at what your move will do, it looks ahead to what the opponent's next move will do. It stands for minimizing the opponent's maximum gain. So when you play a move, your opponent will find their best move, and you want to play the move that their best move will produce not so bad of an outcome for you. In order to implement this, I needed to speed up my find best move algorithm, because it was taking about 12.5 seconds for an average game. Once you do minimax, once you look ahead one turn, you're basically squaring the number of operations you need to process. And so if I was taking 12.5 seconds already, it was definitely not going to work. I wanted to keep the thinking time to under 30 seconds. So I had to speed up the find best moves algorithm. The way I did that was basically tried a bunch of things that didn't work, and eventually one of them did. I don't want to go into technical details, it's very technical, but basically in that cloning process that I talked about, where you make a clone of the game to play the words on, it was taking very long to clone because it was cloning tiles, and the tiles were actually graphics components, the actual tiles that you see on the board. So what I did was I separated the idea of a tile from the actual graphics component, the button, and so the new tile class was just 2 pieces of data, the letter of the tile and the color that it currently was. Once I did that, it sped it up a lot from 12.5 seconds to 0.1 seconds. And so now Minimax is a little more practical. So this is just a little diagram to show you how Minimax works. It's a little bit hard to just figure it out from listening. So same thing from before, I cloned the game, and there are actually 11,000 different clones to play moves on, but I'm just showing 2 examples. Now, if I play thrown, then we make a clone of what happens after thrown, and we play the 11,000 words that the opponent can make. and then we evaluate the end state after the opponent's move. And we want to find, of course, the one with the highest value. Same idea as before. And when I implemented this, which is not too difficult code-wise, I was very optimistic. I figured it would make the program a lot smarter, be a lot more sophisticated. Problem was, when I ran it, it took, instead of 0.1 seconds, I think now it took 541 seconds. So that was, of course, totally unacceptable in terms of how long it took to run. So I was very discouraged at first. I was really expecting it to take maybe 3 seconds, 10 seconds at the most. But when you think about taking 11,000 moves, and then for each of those, trying 11,000 moves for the opponent, that's processing 11,000 square different scenarios. So that's a lot. So I can understand why my computer took some time to think about that. But I still needed to speed it up. So I looked at the Wikipedia article for Minimax, always a great resource, and basically was just looking for anything that would help speed it up. And I found this one little mention of a technique called alpha-beta pruning. And it sounds very complicated, but it's actually a very simple idea. I'll try to explain it with this chart. So alpha-beta pruning makes the Minimax algorithm more efficient by not processing all the branches. Whenever you know that a branch is not going to be helpful, you basically cut it out and stop processing. So this chart shows you the moves you could make, and then 2 of the moves the opponent could make. This ellipsis represents the 11,000 other ones, and then the best min-max value there. So for example, if I played Throne, the opponent could then play the move Groan and turn the min-max value to -5, or Masters, which would give you a value of -2. Now the opponent is playing against you. He obviously wants to minimize your value, give you the lowest value, the worst board at the end. So he's going to pick the -5 one. Now we look at the next word, Groan. Now this thing on the side, threshold, is kind of the fundamental idea of alpha-beta pruning. So that threshold is what we just got here. It's the highest value we've obtained so far for a move. So Throne, the minimax value, what we would expect the opponent to give us would be a -5. So that's the best we've come up with so far. Now the next line, if we play Groan, and then our opponent could play Seats, which gives us a -3 value, or Throne, which produces -2. That's a mistake. That should say -3. He should pick the -3 to minimize his loss. I was doing this very late at night and I made a mistake there. But the threshold then would be -3, because -3 is better than -5. So now we've determined that Groan would be a better move to play than Throne, because our minimax value would be higher, less negative. Now if we look at the next line, we play Seats. He plays Row, gives us a value of -1. That's actually a pretty good number for us. And then the next one is -4. And once we see that, we look at our threshold. -4 is less than -2. So that means we should get rid of this branch, because we know that the opponent always picks his best move. And once we found this, we see that he can pick a move that will give us -4. Since we have this option, which we know will give us -2 at worst, there's no point in exploring the rest of these, because you can already pick a move that gives us a worse value than the other move we chose. So we cut out this branch. And that process happens for all 11,000 branches. And because the threshold keeps increasing the more you process, it really cuts out a lot of branches towards the end. And so the speed reduced for that game I was testing it on from 541 to 4.8 seconds, just because of this technique. Which was great. So now it was practical, and it was a pretty short thinking time. So I tested it, just as I tested the other one. I didn't bother testing my program going first, because in the other example I had already won all the games going first, so I figured now that the program is smarter, there's definitely no chance that the Letterbrain will win if I go first. So I let Letterbrain go first. We played 8 games, and I won 7 out of 8. Not bad. This one, he just got lucky. He really did. I just missed having a winning move by 1 tile. If I had a move that would finish the board, what would bring me to a 12-13, so I would lose. And it ended up being that even with the best move I could make, he could still get a 13-12 the next move. So he won that one. But I do honestly think that was a very rare case. That wouldn't happen very often. And actually, if I go back to the version 1 data, I want to just show that besides just the win-loss ratio, if you look at the length of the games and number of moves, some of these got very long, 26, 42. This one was the longest at 97. That one took several hours. And if you look at the version 2 data, most of these games are much shorter. And that's because now that the program is thinking ahead, for example, if it was going to play a word like container, it might look ahead and see that the opponent would just play containment and take back pretty much all the same letters. So it would play a word instead that locked a lot of tiles so the opponent couldn't take them back. And it tended to use a lot more gray tiles than just trying to use all the opponent's pink tiles because it knows that they can just take them back the next turn. And that helps reduce the number of moves per game. You can also see that the score differences were a lot wider. I generally won by a much wider margin than in the other games where I won most of them by 13-12 or 14-11 or so. So this is the most current version that I have. It's definitely not complete. There's still a lot more things I can do with it. But I'm going to just show you an example now of how it works, what the actual program looks like, because I realize I haven't put any pictures up of that. Do you have any volunteers who would like to try their hand against my Letterpress Victory program? Otherwise, I'll play him. I'll play him. You'll play? Okay, Simon will play. So I have a game open here. Simon, you can you just click the tiles that you want to form your word. Now, it doesn't check if it's a real word, so please just use a reasonable word. And then we'll see what it does. Yep. You're fast. Okay, warthog, good word. Let's see what it comes up with. It'll take a few seconds to think. Okay, that's halfpenny word. See what that does to the board? Okay, Simon, your turn. You can use them, but they won't change to your color. Using the X, good.
This just doesn't change?
No, but you can still use them. Generally, you usually have letters like Q, X, and Z towards it. Oh, you have to clear. I actually ended up taking out the backspace feature because it was really annoying to code and I didn't think it was necessary. You can actually spell expatriate? Good word, Brian. Brian thought of that one. Okay, remember, make sure you're using the right A's and E's except when there are multiples. But yeah, see, you shouldn't have used that blue R. You should have used the white R. But that's okay. Wait. Aren't you missing letters? Okay, that doesn't matter. It accepted it as a word, but it came up with quaveringly. So I'm afraid, Simon, you've lost. So playing against a human, you can see it usually wins pretty fast. It has a little bit wider vocabulary than Simon, maybe a couple words more. That's okay. Okay, so this is one of my greatest challenges in this project, was time management. It was really not so much a case that I was procrastinating, because I really did love what I was doing. The work that I was doing was always interesting, always challenging. It was really more a case of underestimating how difficult things would be. So, for example, the debugging period took a lot longer than I expected. Drafting the GUI took a lot longer than expected. And so it ended up being that I did a lot of work towards the end. As you can see, this is my hours by month. We're required to keep track of all the hours for W.I.S.E, so I just made a little graph of it. You can see the general trend there, and then May, 64 hours. And then by week, you can see that too, an even sharper increase. Last week, I spent 28 hours on the project, and 13 in the last 3 days, just finishing everything up. But there's still a lot more to do, and I will show you some of the ideas that I still have for this project. I would like to speed up the find useful moves algorithm. That's the one that narrows down the words by deleting the subsets. It generally takes a pretty long time right now, between like 40 seconds to a minute and a half, depending on how many words are possible in the board, it takes a very long time, so I want to figure out a way to speed that up. I want to look ahead more plies. Plies just means turns. So right now I'm looking ahead just one turn. It's very effective because the other apps like Letterbrain and like People don't look ahead very far, so it wins pretty much all the time. But I would like to see if I can look ahead more plies without slowing it down too much. Games like chess, for example, the Deep Blue computer, the famous computer that beat Kasparov, looked ahead something like 12 to 16 plies. Now, of course, chess is a very different game. The number of moves you can make are very different, and also the analysis, the evaluation of the board state is a lot more complex because it's not just a simple way to figure out, how good the board is in chess. It's very strategic, very human, actually. And the last thing is maybe take this from Java and write it in C++ and/or develop an iOS app and actually put this in the App Store as a competitor to Letterbrain and such. In general, my future plans, I'll be attending the Carnegie Mellon School of Computer Science in the fall. And other plans for similar work, I've been thinking about doing harder AIs. Like this project was, as Mr. Petrie said, very difficult. A huge step up from what I did before with Hanging with Friends. But this whole idea of writing programs to think is still so fascinating to me that I am thinking about doing more complex games like Monopoly and Risk. Those are particularly interesting because they're not deterministic like Letterpress or chess. Deterministic meaning that theoretically you could guarantee victory from the beginning if you searched every single possibility, which is not practically possible. But each turn you know exactly what will happen. Whereas in Monopoly and Risk are probabilistic, so there's chance, obviously, especially Monopoly, tons of chance. So it'd be really interesting to try and write an AI for that game. Now there are a number of people I have to thank for helping me along this journey with the project. First, Mr. Petris, my mentor. Mr. Petris was my AP Physics teacher, as he said, and I knew he'd be a great mentor because he's a nerdy and curious science guy just like me. And he really, he was always curious about what I was doing, always supported even when he had no idea what it meant.
Most of the time.
And he was a great person for me to just talk out my ideas. And he can attest that sometimes we'd be talking and I would just come up with something and write it on the board, and all of a sudden I had figured something out just by talking to him. Secondly, Mr. Murphy and Mrs. Ferraro, the W.I.S.E teachers. W.I.S.E is an incredible program. I personally learned so much about computer science, about algorithms, game theory, artificial intelligence through this project. And it was the funnest thing I've done probably in all of high school. Also the thing I've worked the hardest on in all of high school. All for a little P on my report card. And of course my friends and family have always supported me in everything I do, whether it's computer science, programming, music, everything. So thank you to everyone. I'd like to especially thank my brother Jesyan, who got me started with Java in 7th grade. He brought home a book and I started reading it, and that's how I really got introduced to programming and started doing this. And finally, most importantly, I'd like to thank my friend Rohit. Rohit basically did half my project. He played all the games against me with Letterpress, which he'll tell you took a long time. With like that 97 move game, we stayed up many late nights playing Letterpress, and he fell asleep 3 times during those nights. And he's just been such a tremendous help to me, one of the most important people in this project. So thank you all for coming. I invite you to download Letterpress if you find it an interesting game, and challenge me. My name is JKnight504. And we have refreshments in the back there. I have 2 copies of my source code. If you'd like to look at it, I'll bring it up there. And you can also play Letterpress against me if you're